Good morning, ladies and gentlemen. Do this now. A light bulb has 80 watts and 120 volts written on its top. How much current would flow through the bulb at 120 volts? What would happen to the brightness of the bulb if it only got 60 volts?
So find the equations you're going to need in your notes and do this now. Pause and go. All right.
All right, so you should have something that looks like this. So we want to know how much current, right? And we've got power and watts. What's that equation?
P is IV, intravenous.
IV. Yeah, I like that. So we just divide by V, right?
Yep.
Okay, so power was 80?
80 watts divided by 120 volts.
Divided by 120 volts. 8 divided by 12 is 8 divided by 12. 120, I mean. We get 0.66, we'll call it 7. 0.667, and we're talking about some coulombs here.
Nope, amperes.
Oh, sorry.
Coulombs per second.
Oh, yeah,
Coulombs per
sorry.
second would be right.
Amperes, sorry. Dang, okay. All right, so that is how much current would flow. What would happen to the brightness of the bulb if it only got 60 volts? Can you
Well,
do some math on this one? 60 divided by 60 volts.
yeah. Well,
I don't think we need to do the math.
well, no. There. In fact, I'm going to say don't do the
Don't do
math.
Because,
Power is current times voltage.
Uh-huh.
And what was that? What was that equation yesterday? Wait a minute. Was it yesterday where we had to? No. What if? Well, I tell you what. It wouldn't be as bright.
Yeah, so it wouldn't be as bright. So, if we decrease the amount of power, it was that changes lab that we did.
Yeah, and what you're going to have here, and what you could do, is what would the resistance be? What would be the resistance? You've got the current. You've got the voltage. Resistance is how much current per volt, right? V equals IR. So divide V by I, that'll give us the resistance.
Yeah, so we got.
Okay, and so that would be 120 volts divided by 0.667 amps. 120 divided by 0.667. And so what's that resistance going to be?
120 divided by 0.667, and we get 180?
180 ohms. So the resistance is 180 ohms. So now...
It'd be the same thing, but with 60 volts?
Yeah.
And I get 90 ohms.
Well, no. What we're talking about here is the bulb itself has some resistance, and we've just calculated what the resistance was. So I think we can agree that the bulb would not be as bright. And let's just leave this up here, and I think there's something that's coming up that'll help us figure this out.
Yeah. Okay, so how could you calculate the power of a bulb if all you had was the current and the resistance?
That's what we're trying to do here, right?
Yeah, so...
Well, no, it's not what we're trying to do, but this is another way to look at it.
So all the next slide talks a little bit more about this, but I'm going to go ahead and write some stuff on the board.
All right.
Okay. I'm actually going to erase this.
All right.
Okay, so we know that we can calculate power using this equation, right?
Yeah.
Okay, but what if all we had was current and resistance? Okay, so we don't have this. All we have is current and resistance. So if all we have is current and resistance, what did we say?
Well, Ohm's law is V equals IR, right?
Yeah, V equals IR. So I could take this IR and I could place it right here, right?
Oh, substitute it for V.
Okay, so now we've got I times R.
I'm too lazy to write I twice.
So let's go I squared times R, right?
That's another way to do it.
Okay, so if you need to figure out the power, but all you have is current and resistance, have no fear. You can still use this equation here. Oh my gosh, that rhymed. Okay. And this is what we just went over. What power is, how we can calculate the potential difference here, and we can just put that right there.
Yeah.
We get I squared.
Boom to boom.
Okay.
All
All
right.
right. So conventional current assumes that positive charge carriers are moving in the wires.
And we're sorry to point this out, but it's just something we need to remind you of. It's really electrons that are moving. However, in textbooks, and you probably will encounter this, you take physics in college, they've got positive charge carriers in the wires. Sorry.
A series circuit has only. Oh, wrong way. Go back. we're ready for our lab now. Okay.
Well, no, that don't go. Let's go back to that.
Oh,
thing.
you're right. Oh, sorry. We're good. Let's see. I said a series circuit. A series circuit has only one path for the current to follow.
So let's make a series circuit.
So let's make a series circuit. Sorry.
Well, first, yeah. So we got the changes. No. What's the name of the lab?
It's called. That's weird.
So boys and girls, get this lab out.
Mr. Boykin and his amazing names.
Yeah.
Okay, so it says make a simple circuit using 2 batteries. Measure the resistance of the round and the oblong bulb separately, which is brighter. Okay, well, we're gonna put them both.
Okay, not yet. No. We'll get to that in a minute.
Oh yeah, okay.
No, we need to follow the step by step.
What does this first part say? Sorry, I didn't read it. I didn't read it good enough.
Well, we're doing the round bulb by itself.
Oh, okay. All
So
right.
take it off the oblong.
Oblong is out. Okay, so make a simple circuit using 2 batteries. Measure the resistance of the round separately. Which one is brighter?
Okay, we can't measure the resistance directly,
No.
so we're going to have to find the current
And the voltage there.
and the voltage. So take off one of the wires here and
I'm going
replace
to
it with the
replace
ammeter.
it with this guy, yeah. Get over here. Bada boom. Bada bang. Okay. So round bulb first. Wait,
Here,
there we go.
there you go.
Okay. So we're in the top part. So we're about 260
260 milliamps.
Okay, let me write that down. So 0.260 amperes.
Yep, 0.260
Okay.
amperes, and now we might got to measure the potential difference across it.
Yeah. Should I just leave this in?
Leave that there,
Okay.
and we'll just.
And we'll latch these on here.
Yeah, we're gonna. So the voltmeter measures the electrical potential difference from one side of the battery to the other.
Okay. Okay. Let me know what it says, Boykin.
That's about no, I beg your pardon, 2.5 volts.
2.5 volts. Okay. So 2.5 volts. This is what I have so far.
So, boys and girls, you've got the current, you've got the voltage, find the resistance while we do this.
Okay. Now, in addition, think about how bright this light is. I mean, just take note of it. It's
Pretty
kind of
bright.
cute. Yeah, it's pretty bright. Okay. All right. So now let's do the same thing, but with our oblong bulb. Okay. So we're gonna leave our setup the same here, but we're just going to put in our oblong bulb. Oblong. Okay. Get in there. Okay. All right. So I guess we don't need this yet. All right. So here we go. So let's get the current running through this bad boy. Oh, I must not be touching the thing right there.
Make sure it might not be screwed in all the way. There
Oh,
you
there we go. Ooh, take a look at that brightness. Is it as bright?
It is not as bright as the
Okay.
other one.
All right. So for amps here, we're at like 90.
So 0.090 amperes, 90 milliamps is 0.090 amperes.
Okay. And I'm just gonna make a little note that this one is bright. Is someone at the door?
I don't know. Do you have paper in your?
I do.
Okay.
Because you know how you're supposed to have it in case of the on
Yeah.
campus. Okay, so next we are going to attach in. We got to measure the voltage drop across this guy.
All right.
All right, here we go. What does it say over there?
That's about 2.5 volts.
Okay, 2.5 volts.
So the
Consistency.
potential difference was the same in both cases.
But
Less current means
current.
more resistance in the oblong bulb, less resistance in the round bulb. So you guys go ahead, use Ohm's law, and solve that for resistance. Do you have the data?
We do.
All right.
Okay. So next thing, step 2. Make a circuit with both white light bulbs wired together in series. Okay. Light bulb number 1.
Okay.
Okay.
Wire goes from one bulb to the other.
And so this is what this looks like.
All right, so there's only one path for current to follow. All right, that's where the wires are.
All right, so this question says, which bulb is brighter?
Okay, I'm gonna put them right next to each other.
Yeah, that's a good idea, Boykin. All right, so here we go. Hopefully I can...
Hold up. Hold up. The round one is not even lighting up.
Huh, oops.
And the oblong bulb is.
That's weird.
What's the name of the lab, boys and girls?
Okay, so...
All right, but what does it mean if one bulb lights up and the other one doesn't? Well, is current flowing through the bulb that's not lit up?
It is.
It has to, because current can't get to the other bulb unless it goes through this. So current is going through the bulb, it's just not lighting up.
So the oblong was dim and the round was no light, right?
Yeah.
Whoa.
Well, the oblong was about as bright as it was before, a little bit less, but it's hard to tell with the lights on in here.
I know, I'm going to say same as before, just so I make a note, and that way you guys know.
Okay, what do we do next?
Measure the current before, between, and after the bulbs. Record results here. Okay.
Okay.
So that means this guy right here, right?
Yep. So what we're going to do is we're going to take.
So we're going to take out this first white wire and we're going to replace it with our ammeter.
Okay, that's the round bulb and the positive terminal.
Mm-hmm. Yes, positive terminal. Thank you. Okay. So I'm going to attach this here.
Actually, you're going to need the red one over here on the positive.
Oh, I see the positive terminal. That's right. Let's go negative terminal first.
Okay.
Because I'm going this way.
Okay.
So we'll just start on this side over here. Why are we starting? How do we know it's the negative terminal, Boykin?
Well, because it says so on the battery here somewhere.
It's got that negative sign, right?
There's the positive signs on the bump.
Yeah.
The bump's got the positive. The other side's the negative.
The black side is the negative side. Okay, so hold that there. You ready for me? And here we go.
That's about 85 milliamps.
Okay, 0.85. Okay, so 0.85, so 0.085 amps, right?
Amperes, yes.
Amperes, like this?
All right, that's between the negative side and the round bulb.
Okay.
Now, put that
White wire back, right?
wire back.
Okay, I'm just gonna work my way around. I'm gonna go to the middle one now.
Let's do the middle one. So take the middle wire off and replace it with the ammeter.
La da da, because it has to be in the current. It has to be in the flow.
It has to be in the current, has to flow through the ammeter, or you're not measuring current.
Yeah. Oh, this is like on the edge over here. Okay, get on there. All right, so you ready for me?
All right, hit it.
Hit it.
Well, that's about the same. That's about 85 milliamps,
Okay.
83, 84 milliamps.
So 0.085 amps.
Yeah.
0.085 amps, okay? And then lastly, we're gonna go ahead and check out the positive terminal. Okay, oops. So I'm gonna replace this guy right here. Put this back here. Boop, 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 boop. And we're gonna measure the positive terminal, which is this side of the battery, okay? And what Mr. Boykin was saying to do before, which is a faster way to do this, is instead of switching out the wires like this, we're just gonna flip the batteries, which works too. You can do either one, okay? All right, and here we go. And
that's about 0.85 or 85 milliamps, so 0.085
like this.
amperes.
Okay. So the current between it was all the same.
Yep.
Okay. All right. So what is a voltage increase across the batteries?
Okay, so
now should I take this off real quick?
Take this off and put the.
Save you for later. Yellow back on.
And what I'm gonna say is let's bite the put the red one on this and the black one over there on the negative
like that,
side.
Boykin?
Yeah, that'll work.
Okay. It's nice when you've got a Boykin here to help you through the lab.
You know, I have. I'm an old man. I've done this a lot.
Okay, so will you go ahead and read that for me?
Okay, so that's about we'll call it 2.9 volts.
2.9 volts. That's pretty good. What is the voltage? So 2.9 volts.
Okay.
Okay. What is the voltage drop across the round bulb and the oblong bulb? Okay, so let's take these guys. Yeah, off there. Yeah, off there. And let's go ahead and do the round bulb first. Boop, 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 boop. You guys want to know what's nice about this book is that it holds the batteries right in place.
They don't roll around the table.
Okay. Okay. Boop, 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 boop. Boop, boop, boop. Okay, so voltage drop. You ready?
Yeah.
Get set. Go. Wait, on. Am I touching it?
Yeah, you are. That's about 0.2 volts.
0.2 volts. Okay, so round bulb, 0.2 volts.
That's the one that's not lighting up.
Okay.
Not lighting up.
Huh. And then,
You do the same thing on the oblong bulb. Light it on either side. We're measuring the difference in electrical potential energy from one side to the other.
oh wait, hold on. Sorry.
And now we got about 2.3 volts.
2.3. Okay, so 2.3 volts. What does that mean? Okay, so what I want you guys to calculate now, and should we just go ahead and do this with them?
Well,
What is the power used by the round bulb?
now they should do that. Power is current times voltage, right?
Mm-hmm.
The current's the same every time. So it's going to be the current times that.
Mm-hmm.
And then for the oblong bulb, the same current
Times
times that'll give you that. And then what's the total resistance of the entire circuit? That's the current through the batteries. Well, that'd be, let's use the voltage increase across the batteries and the current. So go ahead and calculate the resistance of the entire circuit. But, well, you know what? Let's do that one.
We should do them. We should do it with them, right?
Yeah, so that's going to
Let me get it. Let me get a different color here. Okay. Now, should I do it on the paper or should we?
Let's do it on the board.
The board. Okay. Okay. That's kind of what I was thinking. All right. So let me go ahead and erase some of this up here while you guys get your stuff situated. Make sure your numbers all look like mine.
So leave the V equals IR. We're going to need that one.
I should get there.
So just to double check, here's our data. So resistance, how do you solve that V equals IR for resistance?
So V equals I times R. So I'm just going to go ahead and divide by I on both sides. And here we are. Right?
Okay, so the voltage is 2.9 volts.
Okay, so 2.9 volts.
And the current is 0.085 amperes.
Okay, and this is for the round one or the oblong one?
This is for the entire circuit.
Oh, okay. So should we just do we say it's S for series or?
No, just leave it
go
like
for it?
this.
Oh yeah, 2.9 was the whole circuit. I was thinking of the 2.3 one.
That's because the batteries are stupid. They don't know where those wires go.
Okay, so our resistance is 34.1. Do you want to just call it 34?
You just call it 34. 34 ohms.
Ohms. Okay, so this is for the whole thing.
All right. Okay, so let's put the lab aside for now and let's talk about what we've seen.
Oh, wait, Boykin, were we going to answer something else?
Nope.
Okay. Oh, we just calculated the total resistance for the entire circuit. They calculate the power for each one.
Yeah.
Okay, and also don't forget to calculate the resistance up here for each of these.
You know, let's calculate the resistance for each of those right now.
Okay, so so for the round bulb, what's the first number they give me?
Round bulb, it's 2.5 volts divided by 0.260 amps.
Okay.
And
Let's look at that one first. So 2.5 divided by 0.260. Okay, so I get 9.6.
9.6, okay.
Okay.
That's the round bulb. And then the oblong bulb is 2.5 volts and 0.090 amperes.
Do you guys go ahead and make a prediction? Do you think this is going to be more resistance or less resistance?
Well, it's flowing less current. No, yeah, it's flowing less current, so it's got to be more resistance.
Okay, so 2.5 divided by 0.090, it's going to give me 27.8. Okay, so we might not need all these decimals, but okay, so
All right, so that's good. Now let's go to back to our lesson. So you got your notebooks there, boys and girls?
let's do it. Okay, so we ended with this. A series circuit has only one path for current to flow. The current is the same everywhere in the circuit.
And we saw that.
Yeah, we saw that right
when
here.
we measured the current, but when we took each wire out and replaced it with the ammeter. So this is a very important thing. The current is the same everywhere in a series circuit.
What is resistance? It's how hard it is for something, in this case our electrons, to flow through it, through the wires, right? And through the light bulbs.
Yeah, it's easier to run through air than it is to run through water.
Yeah. Speaking from experience. And what does resistance do to the energy of the charge flowing through it? Well, if we look really closely at that filament, right?
Yeah.
And energy has to be conserved, okay? And
Yeah.
the current goes through, and some of that energy is being transferred into heat and light.
Yeah.
Right? And so
It just, yep. And so that's what the resistance. It's hard for the electrons to get through. It takes energy out of them and converts that into heat and light. Okay, now here's something we haven't done yet.
mechanical universe. Okay.
Do you have that up?
Yeah, I do actually. Okay, now do we want to watch it over here? Or
Yeah, we can watch it right here. Go.
let me go ahead and make sure my volume is nice and loud.
Transporters of people,
Full screen?
cargo,
Full screen.
and ideas. And through miles and miles of wire, the flow of information follows from the practical use of Ohm's law.
Ohm's law.
Ohms.
And in much the same way, similar rules lead hydraulic engineers in the design and operation of aqueducts.
What?
Water. Didn't she just make a reference to water?
Yeah.
Those engineers have long known that the rate at which water flows through a pipe depends on just a handful of factors: the slope of the land and the pressure applied, the length and diameter of the pipe, and the viscosity and density of water. In precise analogy, the amount of electric current that flows through a resistor depends on the voltage drop across it, how wide and how long it is, and what it's made of.
The battery takes it up, the resistor takes it down.
The resistance of an electric resistor is proportional to its length, inversely proportional to its area,
Hey, this sounds familiar to me.
and proportional to its resistivity, or its tendency to inhibit the flow of electrons.
Yeah.
This tendency to resist is something all materials have, but to varying degrees. Adding resistors to a circuit, one after another,
Does what?
has the same effect as making one resistor longer.
Oh. Okay, stop that bad
Right there?
boy.
These
Okay. What? Creepy.
No, it's like
Let's
you
go
can't
watch
just
that.
sit there and watch that thing by yourself. It'll put you to sleep and you'll have nightmares.
So adding a resistance in series effectively increases the length of the total resistance.
That's what they just said. And that's like with the potentiometer when we had the other day that had all the wire wrapped around the core.
Yeah, and it could change the length of it.
Yeah.
Okay. The total resistance is the sum of all the resistances in the circuit.
And we kind of see this over here.
Yeah, 27, so this would be 36.
Yeah,
right?
okay.
Which is
And
close.
notice that it doesn't add up. Now,
Yeah.
now, why is that?
Well, we couldn't have made a mistake reading our...
Well, with the series circuit, we had more wires. We had more wires, and each one of those wires has resistance. The electron has to flow through the resistance.
Oh, here, sorry.
Yeah, and so for the equipment that we're using in the lab, it's an approximation here.
Yeah, but it's in the ballpark, right?
Yeah.
Okay. So the idea is, the idea is that this plus this would add up to equal this.
Yeah.
Right? The total resistance is the sum of all the resistance in the circuits.
So, and this is basically what you just got through saying.
Okay, so the resistance in the series circuit is going to be equal to the first resistor plus the second resistor.
And that's called the equivalent resistance. It's
The
like the
equivalent
battery, what the battery experiences.
Okay.
And the battery's stupid. It doesn't know what's connected up there.
Okay, so you have to find the equivalent resistance before you can find the current flowing in a circuit.
Yeah. If you're working on a problem where you've got a bunch of different elements, before you can find the current, you got to find the equivalent resistance.
And you said this was the equivalent resistance?
Yep.
Yeah. Okay. So, so what does that look like? So if the same current is flowing through two different resistors, just like how we had over here,
Yeah.
higher resistance will take more energy.
And we saw that in our lab, didn't we? That the voltage drop across the higher resistance oblong bulb was much larger than the voltage drop across the round bulb. Well, what is a voltage drop? What's dropping? It's the electrical energy of the electrons flowing through the circuit. So if it's harder to get through, the electrons go in one side, they're all pumped up, they got lots of energy. When they go out the other side, they're tired. They've given up a lot of it, but the low resistance, it's easy. It just goes right on. Oh, I'm not tired at all. I only lost 0.2 volts of electrical potential energy per coulomb.
And which one? Well, I'll say that for later. Okay.
So, and here's the evidence. The round bulb has less resistance. It's easier for the electrons to get through. The oblong bulb has more resistance, and it's harder for the current to get through. So it gives up more energy in a series circuit going through the higher resistance, and gives up less energy going through the low resistance.
Sweet. Okay. Now, the potential drop across the element, across an element is the voltage. The potential drop would be the current times the resistance.
Yeah, and we actually measured that with a voltmeter on our lab. But if you're doing a problem out of the book or you're designing a circuit, this is how you find out what the potential drop's going to be.
The potential drops across each element add to equal the potential increase of the source. The ups equal to the downs, right?
Now, the ups is equal to the downs, and this is the law of conservation of energy. And I think if we look at our data here, you've got the oblong bulb is 0.2 plus 2.3 is 2.5, and that's about what the voltage increase was across this. Now, of course, we also have wires that have resistance that also requires voltage to get through, but this plus this equals that.
Okay. So if let me go back to this. So the potential drops across each element add to equal the potential increase of the source. So the ups equal the downs, right?
Well, and so why the negative is here is because these are all downs.
Yeah, and you could switch
and that's an up.
Make a positive and these negative. I think in our drawing a couple days ago we made this positive and we made these negative.
Sure.
It's okay. But the idea is that these add up together to give you what the total potential difference is.
Yeah.
Now, if we need to calculate that, then we can do that using the current throughout the series and multiply that by each of the resistors.
Yeah. And so this is something to go into the toolbox as we go. Well, we should practice. Is there anything more here to talk about?
No, not after this slide. We gave them for homework. They're going to be doing chapter 23, page. Wait, was this in the regular physics book?
It's in the regular physics book.
Yeah.
And it's on page
534.
Page 534 in the regular physics book, number 1, 2, and 3. 1 and 2 are basically the same thing. 3 requires you to see if you understand.
Okay, sweet. Good luck, you guys.
Do that.